Okay, a couple of things in the realm of announcement type fodder. We are in the midst of an open virtual lab that was running because we didn't actually meet on campus for anything on Tuesday. So you have virtual lab 1 open and available to you now. You do not need to meet anywhere to do that lab. So there's no traditional lab meeting that is running this afternoon. That virtual lab is due next Thursday by 11:55 p.m. Okay. Now, despite the fact that we're not required to meet anywhere, I will still be here. I will be in this particular lab space. And if you want to remain, those of you especially who are Thursday lab people, if you want to remain on a schedule and make yourself available to work on the lab and get answers to questions you might have over the lab, I'm going to be here in the traditional lab time this afternoon. So if anybody shows up, I am available. I will answer questions. I will do whatever. Okay. So there's that. Homework is continuing to come online apace. It's coming online at roughly the rate of 1 assignment per class session. So there's homework that's available now that gets into chapter 9 that I'm going to talk specifically about. And if all goes well, I'll actually work out a problem from the homework in class session today. But please, particularly if you haven't gotten on sampling and done the review assignments, get on top of that. Get on top of that soon. You're really going to benefit from having done that. Okay. And when we get back in here on Tuesday, it's my intention to point out a little piece of assessment I have available for making sure you're up to speed with the Chem 1 stuff. Okay. Not a full assessment like we're going to do throughout the term, but particularly for those of you who aren't used to how I'm doing the online assessments in from Chem 1, something that can get you used to that type of format of assessment. Okay. Any comments, questions, administrative matters we need to go through before we get started with our program? Okay. When we left off on Tuesday's meeting, we introduced a new term. And this, question. Yeah. Oh, it's not up there? I've got, you know what that probably means? That probably means I haven't shared the screen with the people on Zoom. Now we're in business. We'd introduced a new term on Tuesday, the concept of specific heat. I'd mentioned on Tuesday that this specific heat is a property of a specific type of matter, an element or a compound or what have you. I'd given you a quick overview of what these symbols meant. Q stands for heat transfer. It's an awkward symbol, I know. We're going to deal with this awkward symbolness as we go through and tell these stories. M stands for mass, like it always has. Delta T stands for change in temperature, and little c stands for specific heat. I think I wrote the expression in this form. And this was the thing that I dubbed the MCAT equation. Those of you who have med school in your future might be thinking about things like this. Does everybody recognize that what I've done here is written the same equation twice in two different forms? All I'm done algebraically to get from here to here is I've actually rearranged the right side, dividing the right side by m and delta t. But we can use these equations complementary to one another. If I know a specific amount of heat transfer, it tends to be really easy to measure the mass of the thing and really easy to measure the change in temperature of the thing to come up with a specific heat. And if I can go to a tabulation of a thing and know the specific heat of a specific type of matter, then I can multiply that through by the mass and the change in temperature to obtain the amount of heat transfer. And so heat transferred is going to be the primary type of energy that I am talking about when I go through talking about energy initially. Okay? And the units of heat energy that I've referred to are the joule. It's abbreviated J. And the units of specific heat that I'm working off of are joules per gram per degree Celsius, or joules per gram per Kelvin. Okay? Now, that's nice. Anybody got a strong sense of how big a joule is yet, or how much energy a joule is yet? The appropriate answer at this juncture is no, I really don't. And we have not given you much of any context to have something to compare a joule to. We use joules on the regular because there are core metric units of energy. And because there are core metric units of energy, they're going to be something I can refer to in a holistic fashion, like I talked about on Tuesday. I can compare one kind of energy measure to a different kind of energy measure using joules. But there's an alternate unit of heat energy that we benefit from because you've heard of it. In most circumstances, you're going to have heard the term for this unit of energy in some sort of dietary or nutritional fashion. How much energy you get out of food. What's that unit? Yeah, it's the calorie. Okay? Now, I want to be very, very careful with how I talk about these alternate units, because as we're going to see in a little bit, these units of energy get used in different ways by different people and they give us trouble because of a little bit of confusion. But I'll go ahead and give you the definition of the calorie as the calorie comes up in chemistry, and particularly in biochemistry, okay? And then make this readable. 1 calorie is the amount of heat energy required to raise 1 gram of water by 1 degree Celsius. The calorie is directly connected to water. Now, that is the first point, I feel like, in my presentation of the matter of this course, where I have connected for you a real tangible thing that a unit of energy can describe. Okay, here's an amount of energy, the calorie. If I have 1 gram of water, a calorie is the amount of energy necessary to kick its temperature up by a degree Celsius. That's a substantial amount of energy because, like we said when we were having our conversation about the water in the iron pot on Tuesday, water resists change in temperature. It takes a lot of energy to raise the temperature of water. So a calorie is a relatively substantial amount of energy. Okay? Now, and let me type this out too, because I don't want there to be any confusion about it. Notice the lowercase and uppercase here. Scientists use the term calorie in one fashion, specifically the amount of energy required to raise a gram of water by 1 degree Celsius. Nutritionists use the calorie in a different way. And you will find, as a rule, that people like chemists and biochemists will always spell calorie with lowercase c, and nutritionists will spell calorie with uppercase c. And those represent 2 different things. The dietary calorie you are familiar with is actually the equivalent of 1,000 scientific lowercase c calories. Which leads to one of the most obnoxious conversion factors I've written in here, that 1,000 lowercase c calories is the same thing as 1 kilo lowercase c calorie, which is the same thing as 1 uppercase c calorie. Really obnoxious. Okay? Nonetheless, biochemists especially are fond of the calorie as a consistent unit of heat energy, and can refer to that type of transfer of heat energy in any number of different ways biochemically. Okay? It does pay to be aware of the lowercase c calorie. Okay? And there are a couple of homework exercises I've got up where I'm going to have you working with lowercase c calories. But ultimately, I tend to have a little bit of difficulty working with the calorie because of this potential for confusion. And there are other circumstances where it's not useful to measure that energy transfer in calories. It's much more useful to measure that energy transfer in joules. I'll get into some examples like that when we're back together on Tuesday. So it's also really important to actually have a conversion factor between calories and joules. Remember the specific heat of water I mentioned in class last Tuesday? That specific heat of water was 4.184 joules per gram per degree Celsius. That 4.184 is the specific heat of water. It is the amount of energy required to raise 1 gram of water by 1 degree Celsius. Therefore, the specific heat of water is a great way to remember this conversion factor between calories and joules. 1 calorie is equal to the specific heat of water. 1 calorie is the same as 4.184 joules for every gram of water for every degree Celsius. Okay? One thing you should be pulling out of this is that the language that surrounds heat transfer is really particular. Okay? And it's really difficult to keep a handle on the language of heat transfer. That language is used in words, obviously, but that language is also used mathematically. Okay? And so much of what I'm talking about today is the type of skills that you need to have in hand to take a problem, to read a problem, and to interpret the information in that problem. And distinctions between a lot of terms that might sound similar that have really distinct ways to get it between. Okay? Let's talk about a different example of this type of language distinction. Back to where we were when we started. The specific heat is a property of a specific kind of substance. Whether that substance is a metal like iron or a compound liquid like water, or whether it's something that's more composite and more consistent in nature. I mentioned the story that I told about this particular pot of water and how you'd much rather touch the water than touch the pot. And the reason you'd much rather touch the water than touch the pot is what's happening to the temperature of the water compared to the temperature of the pot. Yeah, the water is more resistant to temperature change than the iron pot is. And so the iron heats quicker than the water. Okay? This is nice. This is true. When's the last time anybody heated water in a pot full of iron? You don't tend to actually use iron pots on a stove much these days, do you? The pots seem to be more silvery in color, right? Maybe more stainless steel like. Or if the pot is really fancy, the pot is got the stainless steel on the side, but it's more copper-like on the bottom to get heat transfer going more effectively through it. And it's not a simple all made out of one stuff. It's made out of many different stuffs. If it's made out of many different stuffs, this specific heat becomes less and less useful to us. Put another way, or given another example, when we actually start studying this heat transfer in the lab, what we're frequently going to use to study the heat transfer is a calorimeter. And this calorimeter is going to bear a really strange similarity to a coffee cup. The same type of coffee cup you'd get from Cream Cup. Okay? Paper cup. Maybe a bit of insulating plastic stuff on the outside of it so it feels a little bit rougher than just a simple paper cup. Plastic lid to keep the heat in. Okay? Paper and insulating and plastic, I'm talking about multiple different things, right? The specific heat applies to one consistently, specifically known substance. A coffee cup like that is made up of many different substances put together in a really unique way isn't something that I can use the specific heat with. And I need another quantity to work with here. And that other quantity is called the heat capacity. The heat capacity is represented by a capital C as opposed to the lowercase c that I work with when I deal with specific heat. And the heat capacity is put together in such a way that mass doesn't matter. The units of heat capacity are very simply joules per degree Celsius or joules per Kelvin. No mass component in there at all. And I'm going to use heat capacity to describe what goes on in a specific unique device, a specific pot assembled a specific way, or a uniquely assembled coffee cup. Okay? Now, I'm going to get myself into trouble with the word specific if I use it too carelessly, because specific heat is referring to here. Right. Right. Don't you hate it when the professor can't use the technology? Typically, specific heats refer to elements or compounds. And it's a property of a specific type of matter. On the other hand, the heat capacity is a property of a unique object, like a pot that's composite of two different materials, or a unique assembly of objects, like the coffee cup with the insulating material on the outside and the plastic lid. Now, we've dealt with other properties in General Chemistry 1, where we draw a distinction between a property of a specific type of matter and a property of a unique object or assembly of objects. When I talk about a property of an element or a compound, what other properties that we've studied are unique to specific elements or compounds? There's one at the front center of my mind, but I'll take any example you got. I got something in the chat. Brianna comes up with density, which is a very good example to come up with here. Okay? Density is a property of an element or a compound. Okay? I can take a specific solid that's a metal, and that density is going to be the same for every selection of that specific solid metal. Okay? Gold has the same density no matter how big the piece of gold is. Okay? Water has the same density no matter how much water you got. Okay? But I can have a small mass of water on the one hand, I can have a large mass of water on the other. We say density is an intensive property because density is a property of a specific type of matter. But mass, we can measure mass of any old thing. And mass is extensive. Likewise, specific heat is an intensive property. Come on. There we go. And heat capacity is an extensive property. If it's a property that's the same for a type of stuff, no matter how small or big the amount of stuff is, it's an intensive property. If it's a property you can measure for any collection of different stuffs, or if it's a property that changes with the bigness or the smallness of the specific type of matter, it's an extensive property. And specific heat and heat capacity are one key example of this distinction between intensive and extensive properties. And as we go through the term, I'm going to come back to these terms again. Intensive and extensive are not terms that are going to come up in the homework immediately, okay? But I will come back to these terms as I go forward. Okay? So how do we use these specific properties? How do we put these properties into problems and use them to solve problems? Well, let me come up with an example here. The typical heat capacities of the coffee cups we'll come across in the lab are going to be between 10 and 15 joules per Kelvin. Let me just pull 13 joules per Kelvin as a nice convenient value. Okay? Hmm. Coffee cup calorimeter is given a heat capacity. Oh God, behave. There we go. When an amount of water is added to the calorimeter, the temperature of the calorimeter changes from 27.8 degrees Celsius to 20.9 degrees Celsius. How much heat has been transferred? And I'm not being really specific yet about how I'm referring to that. I'm just saying how much heat has been transferred in this experiment. Let me extend this a little bit further. I can never get this exactly right. That's good. That's good. That keeps all the units together. Okay. What equation have I given you thus far that has heat capacity in it? I didn't mean to not wait on you to give me an answer. I just got going and I kept going. Okay? The definition of heat capacity is big C equals Q over delta T. Okay? What symbol represents heat transferred? It is Q. Yes, absolutely. Okay? So, I need to rearrange this equation for Q. How do I get Q by itself? Multiply both sides by delta T, absolutely. Okay. I'm given the heat capacity C. That's 13 joules per Kelvin. What's delta T? Yep. How do I measure the change in temperature? What am I subtracting? You are not subtracting 27.8 minus 20.9. It's the other way. Yes. Why is it the other way? The difference represented by a delta is always representative of which temperature minus which temperature? Not higher minus lower. Say again, Justice. Not lower minus higher. Anytime you have a delta, the difference is final value minus initial value. Every time. Okay? So when I write delta T here, this problem says the temperature of the calorimeter changes from 27.8 degrees Celsius to 20.9 degrees Celsius. It started at 27.8, it finished at 20.9, okay? So delta T is always T final minus T initial. That's why I'm going 20.9 degrees Celsius minus 27.8 degrees Celsius. Okay? If you get nothing else out of me today, this is the one thing that I absolutely positively want you to carry with you. Anytime you see a delta, that immediately tells you you're taking final quantity minus initial quantity. Any questions about that? Okay, 20.9 minus 27.8. Okay. What did I forget to do? If I got my units for this heat capacity in joules per Kelvin, what do I need to do? Yeah, I didn't convert stuff to Kelvin. I better convert stuff to Kelvin, shouldn't I? Just for fun, let me keep this over here and let me do my delta T in Kelvin over here. Okay? How do I convert 20.9 degrees Celsius to Kelvin? At 273.15. Okay, I'm going to have that 0.15 running around, especially when I got circumstances like this. 20.9 plus 273.15. My calculator tells me that is 294.05 Kelvin. Okay, we good with that? T initial 27.8 plus 273.15. That's going to get me 300.95 Kelvin, right? What's 294.05 Kelvin minus 300.95 Kelvin? The same thing. How did that work? Yeah, I just added the same 273.15 to both temperatures. I got the same quantity out for delta. If it's a change in temperature, a change of negative 6.9 degrees Celsius is the same as a change of negative 6.9 Kelvin. That's pretty wild. Okay, here's another thing to file away about temperatures. If I'm interested in an absolute temperature, a temperature at one instant in time, I need to get from degrees Celsius to Kelvin, I have to add the 273.15. Okay? But if I'm interested in changes in temperature, a change in temperature in degrees Celsius will be the same as that change in temperature in Kelvin, quantitatively. Okay? And you can always convert the temperatures to Kelvin to demonstrate that, but you need to convert both temperatures. What you shouldn't do is convert a delta T from degrees Celsius to Kelvin. That'll get you into trouble. Okay? So your temperature conversions, when you do a delta, should look like this. And eventually you will recognize that if you've got the temperature change in degrees Celsius, you've got it in Kelvin as well. And the heat transferred here in this circumstance is going to be 13 joules per Kelvin times negative 6.9 Kelvin. The Kelvins cancel. Clear. 13 times negative 6.9 is equal to negative 89.7. That's going to round very nicely to negative 90. Yeah. Okay. Here's another really important question. What in the world does that negative mean? What is that negative telling you about the heat energy in this calorimeter? Let's go back to the statement of the problem. The temperature of the calorimeter changed from 27.8 degrees Celsius to 20.9 degrees Celsius. It changed that way when water got added to the calorimeter. Well, what does that probably tell you about the water that got added to the calorimeter? It was probably pretty cold, right? And what probably happened to the temperature of that water when you added it to the calorimeter? Yeah, it probably went up. Okay? Think of that in terms of heat. When the colder water was added to the coffee cup released heat energy. The evidence that it released the heat energy was the coffee cup got colder. That heat energy had to go somewhere. Where did it go? Into the water. Absolutely. So I can say, come back here. So I can say something more precise about the way that this heat, what this specific heat transfer means. Okay? Now, because we know that that energy is released, something else is going to be absorbing that much heat. And that's obviously going to wind up being the water. Okay? This is the core of the discipline of calorimetry. Calorimetry is a little corner of thermochemistry where we're just studying heat transfer. We're studying what stuffs release heat in a situation and what stuffs absorb heat in a situation. That's what calorimetry is. Calorimetry has sign conventions. If Q is negative in a calorimetry situation, the heat described as being released by an object. And if Q is positive, then the heat described as being absorbed by an object. And when we do these types of situations, when we study heat being released and absorbed, we know that we're dealing with at least two objects in a system. And whatever's being released by one object is being absorbed by another. And for that very reason, what we need to do is recognize that there's a fundamental way that we describe the behavior of systems of this sort. There's a fundamental equation of calorimetry. A fundamental equation to describe all heat transfer that happens in the universe. And that story is this. If the system is closed, that is, if all the heat being transferred is confined within the system, then the sum of the heat absorbed and the heat released must be zero. If the system is closed, then the heat absorbed is going to be positive. The heat released is going to be negative. Something or some things are taking up the heat and changing temperature, showing some other evidence of absorbing the heat. And something or some other things are showing the evidence of releasing that heat by lowering in temperature or something else. And as a result, the heat absorbed and the heat released are going to cancel one another out. Okay? Questions about that? Okay. Got about 25 minutes left. Shall I show you an example of the problem from the homework? And a particular problem that, again, is going to dig deep into this mathematical language and where I'm going to want us to be able to interpret mathematical language here. Okay? And let me take the Zoom and stop the share here and bring up the share of a homework problem here. Okay? Okay. At constant volume, the heat of combustion of a particular, I'm going to copy this over and I'm going to give you time to copy this down. Constant volume, the heat of combustion of a particular compound is negative 3169.0 kilojoules per mole. That's new. When 1.775 grams of this compound with a molar mass of 186.07 grams per mole was burned in a bomb calorimeter, that sounds fun. The temperature of the calorimeter, including its contents, rose by 6.637 degrees Celsius. Was the heat capacity, also known as the calorimeter constant of the calorimeter? It wants the answer in kilojoules per degree Celsius. Okay? Let me copy this over. So I'm going to copy this. I'm going to do a little stunt with the sharing. Get back to my whiteboard and copy this into a block in the whiteboard. That's it. Now, there's a new bit of language in this that I want you to be aware of, because you're going to hear language like this again as we go forward in the course. That language is heat of combustion. I take some amount of this particular compound, it's actually problem says 1.775 grams of this particular compound, and I put it into the calorimeter, and it's going to release. Now, everything we've been talking about thus far has been joules of energy, right? And I just talked about a particular calorimeter that would absorb 13 joules per degree Celsius of temperature change. Okay, and I talked about an energy transfer of 90 joules. This is negative 3,169 kilojoules. This is a beast amount of energy. Okay. Now the question's asking for the heat capacity of the calorimeter. What's our equation for heat capacity again? C equals Q divided by delta T. Okay, so if we've got Q and we've got delta T, we've got C. The temperature of the calorimeter, including its contents, rose by 6.637 degrees Celsius. Hey, we've got delta T. We're halfway there. And we just got to figure out what to do about Q. And the way that we're given information about Q is new. Negative 3,169.0 kilojoules per mole. Now, there's no per mole in my report of this heat capacity. I've got to do something to get rid of these moles. What do you suppose I can do to get rid of moles? The problem tells me I have 1.775 grams of this compound. And then it turns around and tells me that I have the molar mass of that compound. Yeah. So this is some situation where I can go back to Gen Chem 1 and think about changing grams per moles. Okay? This particular value of this heat of combustion in kilojoules per mole tells you if you have 1 mole of this stuff, you're going to release 3,169 kilojoules of energy. I have 1.775 grams of this stuff. I'm going to make the proposal that I have a little bit less than a mole. I ought to figure out how many moles I have. Let's do that. I have 1.775 grams of the compound. How do I convert it to moles? Yeah, I'm going to divide out 186.07 because 1 mole of this compound has 186.07 grams. And the grams can cancel out. Okay? So how many moles is that? 1.775 divided by 186.07 is going to be a really pipsqueak number of moles here. And this is 4 sig figs and this is 5 sig figs. So I've got a whole lot of sig figs I need to report here with leading zeros to boot. 0, 0. And I'm going to report 95394 moles. Okay? and take that number of moles and multiply it by my negative 3169.0. And that's going to give me a Q that is equal, keep the colors consistent. It's going to give me a Q that's equal to negative 30.230 kilojoules. Okay. So it's a tinier amount of the stuff in a mole. So I'm not releasing as much energy as the whole negative 3169 kilojoules per mole. I'm still releasing a lot of energy. Okay. And delta T is given in the problem. 6.637 degrees Celsius. Oh, wait a second. Let me do something before I say that, because this is really important. Okay. This specific Q is a Q released. I know throughout this entire story that it's a Q released because of the negative sign up front. What I want to do is I actually want to call this a Q released. I'm going to sneak that REL subscript by my Q here. This is the energy that's released by the reaction. Now, where does that energy go? Go back to the problem again. When 1.775 grams of this compound, molar mass weighs 6.07 grams per mole, was burned in a bomb calorimeter. And implied in that burn is there's a reaction happening that's releasing energy. The temperature of the calorimeter, including its contents, rose by 6.637 degrees Celsius. So the reaction releases heat energy. Where does the heat energy go? Who's got it in the chat? It goes into Q, but it goes into Q for a specific device. What device? The calorimeter, absolutely. Okay? So what I'm going to do here is I'm going to represent the Q going into the calorimeter as Q absorbed. And if the calorimeter is releasing 30.230 kilojoules of energy, how much energy is the calorimeter absorbing? A positive. If it's absorbing, the Q is positive. But yes, Q absorbed is positive 30.230 kilojoules for a temperature change of 6.637 degrees Celsius. And when I work that specifically out, the heat capacity of the calorimeter, Q over delta T, equals 30.230 kilojoules over 6.637 degrees Celsius. And that is equal to 4.555 kilojoules per degree Celsius. Okay? Now, I always do these on the fly, so I need to actually go back to the sapling problem and I need to check the solution and make sure I did it right. Oh, show the feedback. It's not revealing the answer. Okay, the other way I can make sure that this is going to happen is I can type this answer in, and if it is correct, it's going to tab over to the solution. If it's incorrect, it's going to tab over to incorrect feedback. So let me check my answer and see if it tabs over to solution. There it is. Okay, that's good. And can I show the solution here? Going down the page. Nope, I can't. Phooey. I was meant to show off that it was actually legit. Now, if I'd open it back up, it's going to regenerate the problem. Sapling did say I got it right. It doesn't give the instructor the happy little check it gives you as a student, though. Okay. Now, when you see a problem like this in your homework, you will see the same setup of the problem, but you'll see different values. And you're going to need to go through the same type of calculation for your own values to come up with your own answer. Okay? Any other questions about this scenario? Okay, I'd like to walk through very quickly one additional scenario that I want you to be aware of as you get into the homework. And this particular problem is not written out just so in sampling. It's embedded in a simulator. And the simulator's pretty cool. And it's worth the extra time it gets you working through the thing. But the type of problem that I'm talking about here is going to set up like this. Am I not sharing? Thank you, Haley. I'm going to stop a share and reshare. There we go. Is that better, Haley? Thank you, y'all. Oh, now I've just minimized the whiteboard. I'll get everything right one of these days, y'all. I'm doing this at the very end of class too, so it makes it even more obnoxious. I was hoping I'd be able to condense the question down a little bit more as I typed it out. It may well wind up being that we take the bulk of the rest of the hour just getting this question written down and talking through the particulars of the question rather than getting anything accomplished towards the solution. But I wanted to bring this specific problem to your attention as a class because this type of scenario is one of the practical uses of calorimetry. Finding the specific heat of an unknown when you have it not just in a calorimeter, but you have water in the calorimeter. And so the most important question I can ask about this scenario as you get it written down is going to be, what's absorbing heat? The metal starts out really, really hot. The calorimeter starts out kind of cool. What's absorbing heat? All right, let's ask the opposite question, see if we can make this clear this way. What's releasing heat? Okay, let's make sure we've got releasing and absorbing specific. Okay? If something is absorbing heat, its temperature is going to increase over the time of the experiment. If something's going to release heat, its temperature is going to decrease. So the release of heat is in the stuff that's decreasing temperature. What thing's decreasing in temperature over the experiment? The block of metal is decreasing in temperature. The block of metal is releasing heat. Okay? So, Q released corresponds to the block of metal. That means, Nate, what's absorbing heat in this experiment? Both. Okay? And that's what makes this particular story a little bit difficult to conceptualize. Is the thing that's absorbing heat energy is both the water and the calorimeter. Okay? So what we're going to wind up having to do as we solve this problem is we're going to wind up having to compute both the heat absorbed by the water and the heat absorbed by the calorimeter. And then we're going to have to use that information to get us to the heat released by the block of metal and therefore the specific heat of the block of metal. Okay? If you're the type of person who likes to gun, take a shot at this problem before we get back into class on Tuesday. And there, like I said, there's a simulator in the homework that demonstrates what goes on in this type of scenario as well. Okay?